Well, hi, I'm Josh Rosenberg. I'm a faculty member at the University of Tennessee in Knoxville. And maybe Megan, Clement, Alfredo, and then Enu, Jin, and Andy. Could you all introduce yourself briefly?
Sure. Hi, I'm Megan Atha. I'm an assistant professor at Florida Gulf Coast University in Fort Myers, Florida. And I kind of got recruited by Susan Hibbard, who was one of the panelists at the Laser Institute this last summer. And so I work mostly teaching master's students data analysis and learning theories, that's like that stuff. But my research is on creativity and STEM competitions.
Well, thanks, Megan. Clement?
Thank you, Joshua. I'm Clement Yeju, Associate Professor of Biology at Florida Agricultural and Mechanical University. I used the workshop this summer, to enhance my ability to analyze electronic health data, especially in the area of breast cancer, prostate cancer, and COVID-19. And I look again forward, to get more experience, so it can really help me to use to collect more data set and look at some of the factors that contribute to health disparity in the area of COVID-19, breast cancer, and prostate cancer. Thank you.
And you, and sorry if I'm not pronouncing your name correctly, looking forward to hearing the introduction.
Hey, everyone. My name is Anu Zhou. I'm Senior Research Analyst at the Council Graduate School. So my research focus on graduate education and looking at master's and doctoral students. Also looking at STEM education as well.
Great, thanks. I've got Alfredo, and then Wei, and then Andy.
Hi, everyone. Alfredo Leon, Assistant Professor of Biology at Miami-Dade College. My area of research is I'm focusing mostly on social presence and how our students interacting in the remote synchronous way, and trying to see how we can leverage certain tools, especially social network analysis and things of that sort to gather more information. I've also been playing with a little bit with AI and seeing how we can facilitate instructional design and instructional development on the faculty side using some of those tools. But that one is very early on, so I've just been playing with that pretty much. Very nice to be here.
Hi, everyone. This is Wei. I'm a new PhD student of learning design and technology of the University of Tennessee. And what I'm doing is collecting a lot of AI policy from different kind of types of university and analyze their policy and see what comes out. And I'm a newer in education technology area, so happy to learn from you guys. Thank you.
Welcome, Wei. Andy, and then Mia.
Hi, everyone. I'm Andy Parra-Martinez. I'm a postdoc at the University of Arkansas. Currently, my research is on talent identification in the fields of education, sports science, and management. And I want to learn machine learning to see to what extent it can help us do better identification of gifted and talented children.
Thanks, Andy.
And I'm Maya Williams. I'm at the University of Wyoming in learning design and technology. And I think I did a couple classes when we were face to face. I'm still trying to wrap my head around this one. So I'm joining online too. So
Great, welcome, Mia. You're welcome back. And hi, Jen. Jen, we're briefly doing introductions, if you don't mind. Just name, affiliation, anything else you wish to briefly share.
Is it my turn?
It sure is.
Oh, okay. Yeah, I was in something, so I just tried to log back. So this is Jean. So I'm from University of South Carolina. Yeah, I'm in cohort, and this is summer. Yeah, I went to laser. So I
Great.
haven't been to the machine learning like in face to face. So I just try to learn more. I feel like I did some machine learning already, but not in the machine learning, like it's different terms, but just to learn the language, everything. Okay.
Yeah, great.
Yeah. Okay, I'm done. Thank you.
Sounds good. Yeah, welcome, welcome. Good to see you again, Jin. So everyone, glad you're here. Machine learning is the topic. I'm gonna be kind of joking here. I think my goal is to convince everybody or remind everybody why you shouldn't use machine learning today and why I shouldn't either. I say that just because machine learning still is kind of in right now, and we can easily think of machine learning as a cool methodology we should instinctively embrace because it's new and powerful. But that doesn't mean, as I'm sure you're thinking, it's necessarily the best methodology or data analysis technique for our particular study. So when you find a study that really is a good fit for machine learning, that's awesome. But often I myself, and I've seen others too, be drawn to machine learning when it's not necessarily aligned well with your the purpose of your study or your analytic goals. So I'll try to I said that too strongly at first, but in seriousness, we will engage critically about around questions about when machine learning is useful, why it's useful, and when it might not be as well. Some of the best discussions we had in the summer and or in the last few summers have been more critical discussions about machine learning, really diving very deep into the fine-grained specifics about what machine learning can and can't do, and when an, let's call it explanatory or traditional or inferential modeling approach, think about a regression and its extensions, might be a better fit, and when it might not be. Just like literally having like on the whiteboard, like regression, prediction model, or machine learning. Lots of synonyms for both of those, but let's say regression and machine learning, and just walking through the benefits and drawbacks of each of those. So I hope we can do some of that today. Logistically, what we'll do is I'll share some slides. There'll be some time for discussion though throughout. And this is followed by what you might notice in the calendar are office hours. Basically open time. I don't expect us to use the whole hour necessarily. Just based on past experiences, but that time will be open for us to talk about your study. You can get some feedback from me or from others in the group then. So I'll try to keep the presentation and discussion, that first part, to no more than 1 hour, if that sounds good. So no later than 4 p.m. That'll be the more didactic part, and then the second part will be more open-ended in nature. Okay, how does that plan align or not align with your goals for today or your understanding of what today is about? I welcome honest thoughts here.
Well, I appreciate the basic intro since, I didn't get any of it over the summer, so that aligns well for me.
Okay, thanks, Megan. All right. Well, if you want to follow along, the easiest way to follow along is through this URL, which I will share with you in the chat. I think that takes you to the right spot. Yeah. So that's the easiest way to follow along with the slides. One other thing I'll mention is I'm going to send you a link to the GitHub repository too. So if you want to complete the learning lab, and as a reminder or as new information, the learning labs are the more independent focused parts. You'll need access to that GitHub repository to do that. So just to kind of make sure everyone's oriented, and especially if you're really into machine learning and you want to follow up, it'll be good to have this as a home base here. So this is a GitHub repository with all of the materials for the machine learning module. And the module has 4 learning labs. And one thing, so there's a lot of things I could do better and that we could do better with Laser. One thing I'm really proud of is just the organization of the 4. This was based on iterating over a couple of years. So the content, you can decide if it's any good, but I think the order of starting with this question, how is prediction different from explanation? A really foundational question. Moving into how we interpret a machine learning model, making our machine learning model better, and then what to do when we don't have training data. I'm really kind of pleased about the order of these. So you can decide if you agree, but big picture over the next 2 to 3 months, we'll be walking through all 4 of these. So today we're focused on this question, how is prediction different from explanation? So just as a high level summary before we get into the slides, we have some data, we want to develop a prediction model. So in that case, we will typically turn to supervised machine learning. I'll define that in a minute. In particular here, we'll explore how we can train a computer to predict students passing or withdrawal from a course. And we'll use a pretty cool data set, the Open University Learning Analytics data set. This is a freely available data set that has data from around 30,000 students and their participation, enrollment, and participation in courses offered through the Open University in the UK. And even though it's only 30,000 students, there's what you could call like clickstream data or activity data that is a recording of the number of times students interacted with different elements of the learning management system by day. So it's pretty fine-grained data. How many times students access any part of the learning management system, from a file to a discussion to the syllabus to particular pages of some activity or task per day per student. And that's a more than million row data set. So it's kind of a cool data set to be using. Okay, we'll dive in. Any questions actually? Sorry, I should have paused. Any questions on this part before we dive in? All right, and I saw one more person joined. Hi, Hanwei. Hanwei, for the sake of time, if you want to really briefly say hi and just your name and affiliation, we can just keep rolling with things here. Thank you for joining today. No problem. No, we can just boogie. Hanwei, feel free to say hi in chat when you get a chance here. Welcome here. I'm glad you're here. Okay, so just as a reminder, everything can be accessed through right here. And we're going to focus on the slides, that first part, that first link here. All right, can you all see my screen, by the way? Is that working okay?
Yeah. Yes.
All right. Thank you. Great. Thank you, Clement, and thanks all. All right, so we're focused on prediction. So this is just a recapitulation of what we just talked through. Here's the plan for the next 45 minutes or so. We'll have a discussion. We'll talk a little bit about learning analytics data. We'll talk a little bit about this key distinction or key element of machine learning, which is making predictions. We'll have a code along. So in the code along, that'll be the more interactive part where if you want, you can follow along in your own RStudio and run code. We'll have another brief discussion, and then I'll talk about what you can do next. It's a little different than the summer. And Wei and Hanwei, glad you both are joining today. This is, as everyone else knows, part of the Laser Institute. In the Laser Institute, it's this week-long summer institute. We have this independent part following the presentation. So that's totally, everyone is up to their own liberty to decide whether to do that. Okay, so here's a brief review before we start with a question here. So if you have coded data or data with a known outcome, that's a really vague description. I recognize that. But if you have data with some kind of outcome, what's an outcome? It's whatever you say it is. It's students passing a class. It's students' final grade. It's a score on an assessment. It's a qualitatively assigned numeric score from a constructed response evaluation. It's students successfully graduating, anything that you can consider to be an outcome. And with that outcome, you want to do one of these 3 things, then you'll be in this bucket that is referred to as supervised machine learning methods. So you could think of supervised machine learning as a flavor of machine learning, one common flavor of machine learning. So those 3 common tasks are, there's that P word again, predict. So if you want to predict how students with similar data who don't have a known outcome yet perform. So this is a classic learning analytics example of, let's say we have data from 10,000 students. We know whether or not they passed a class or whether or not they graduated from their degree program. And we want to use data from other students who haven't graduated or dropped out yet and make a prediction about how they'll do. This is a classic learning analytics application in higher education. And there's also many examples of this at the K-12 level. Second, you want to scale up coding you've done. So let's say you and your team have qualitatively coded 1,000 assessments. but you have assessment responses from 10,000 students, and coding those other 9,000 would take hundreds of hours. What do you do? If the machine learning is good enough, then you can scale up the coding you've done. You can automate it by using the 1,000 coded responses to code far more. Use that as what we would call training data to train a model or an algorithm to make predictions on new responses without a code yet, new outcomes rather, or I'm sorry, new data without that prediction made yet or that code assigned yet. And then lastly, if you're interested in some kind of intelligent tutoring system or something that provides instant feedback either to instructors or learners, then supervised machine learning might be a good bucket to be in. Does anyone have any example you'd be willing to drop into the chat about anything you've encountered in your research or in any other element of your work that you think is an example of something like this, something you could call supervised machine learning? You can say it out loud too. We're a small enough group.
Okay. So I had collected some data from kids who answered divergent thinking tasks.
Okay.
And two colleagues in my division at APA said, hey, can we get your human ratings on those tasks that we scored for creativity? And they're using it to, this is kind of why I signed up for all of this. I want to understand what they're doing. But they're training something called moats to generate creativity scores. You know, they're using my data to help train the platform, the algorithms. So
Yeah,
that
cool.
So I think it's the same. I think this is your second use of the supervised machine learning. The
Cool.
training.
Thanks, Megan. And yeah, sorry. Please feel
No, is
sorry.
that right? Am I getting that right?
Anyone have any thoughts? Agree or disagree? I'll put on my science teacher hat here. Anyone agree or disagree with Megan's contribution to the class? Does that sound like more like this than not? Or does it sound like this? Disagreement's welcome.
I'll
In
put
the
it in
chat.
the chat, then you can explore.
Thanks, Megan.
Mm-hmm.
Well, I'll put myself out there. I think that absolutely sounds okay. Alfredo agrees. Okay, thanks, Alfredo.
Thanks, Alfredo.
Yeah.
I just wanted to put out something out there.
Just make this teacher move on, please. Make this person move on. Yeah, cool. It sounds so. I think part of the premise, and just to emphasize this, Megan, is that qualitatively coded data is very valuable, and we see this in discourse around AI and Chat GPT and the like. One of the biggest challenges for developing these systems is accessing good data, and data that is for research can often include a lot of high quality information that can be used for other things like this system that you shared. Thanks for sharing that. I'll check that out after. Great. Okay. Anyone else have an example of something that you think might be an example of supervised machine learning?
I have a question though.
Yeah, please.
So chatbots that are trained, these chatbots that are trained with the platforms or the framework of ChatGPT, and they're given these answer sets and trained with those answer sets, is that the provide timely or aspect of machine learning?
Oh, good question. Was that Alfredo? Sorry, I didn't see the video. Yeah, thanks.
Yeah, no worries.
Yeah, good question. So I don't want to oversimplify what something like ChatGPT or a chatbot does, because I think they are a little bit more complex. But there's a connection. So my understanding is that something like ChatGPT is based on a model that is iteratively predicting the next word in a series of words. And you can replace word with other things. So how it works with math, I think, gets a little bit more complex. And I think this is why it's sometimes really bad with math, but predict the next word. And my understanding is that ChatGPT is basically a souped up linear regression in that you're predicting the next word using a regression, but the regression is a neural network. And the neural network has something like 1 trillion coefficients, and it's trained on a data set of unimaginable size. So I think in principle, yes. But as others, including you, might have greater knowledge of me than there's also other elements of how ChatGPT works too. So there's this technique called reinforcement learning with human feedback that was used to fine tune how ChatGPT worked. And I think that's what distinguishes ChatGPT from GPT-3 or GPT-4, kind of the underlying model. And then this chat interface is the way they made the model a better bot through this reinforcement learning with human feedback. So I think it's like a neural network with tons of parameters trained on tons of data, plus that reinforcement learning approach, which I'll point out is not a supervised machine learning method. It's another bucket. So we can think about like at least three main buckets: supervised, unsupervised, reinforcement methods. There's a few others as well that are more esoteric flavors.
Thank you.
I'm glad you asked that. Yeah, and I think maybe a fun project, Alfredo, is like a fun use of an hour or so is to try to dive deep into the weeds of how ChatGPT works. And I think part of the magic, and then also sort of seen behind the curtain, Wizard of Oz style, is learning that these models aren't that different from other common machine learning or even other statistical models that are commonly used. They're distinguished more, in my understanding, by the size of the training data and the complexity of the model. I've read. Oh, sorry. Go ahead after you.
No, the reason why I was asking was because I've seen the setting up of chatbots where you're using that ChatGPT platform as the framework for the chat, setting, and you can actually set how quote unquote creative ChatGPT's answers are. So you can actually lower that, and recommendations are keep it between 20 and 30% or whatever that number is, so that it doesn't get too creative and it remains within the parameters of what it is that you're giving it for it to answer, rather than start coming up with random answers that it's creativity or hallucinations at some point.
Yeah, I think we can think of that as being similar in aim to that reinforcement learning step, where we're making this a better bot. Like it's always cheery, and maybe it can be fine-tuned to be less willing to say things that are just completely fabricated. Yeah, glad you brought that up. Yeah, we should be talking about ChatGPT. And Wei, is there anything you'd like to add on this? I know you've been doing some deep dive into ChatGPT. I'm sure many of the people in this group have experience with it and knowledge of it.
Yeah, actually, I collected a lot of university policy about ChatGPT, and also what I have a GRA work related to whether the instructors or the teachers use the ChatGPT, and most over maybe 70% of the instructor was surprised by the GPT function, and they try to use the ChatGPT for their like course design or reflection assessment. So that'd be cool.
Yeah, I'd love to hear more about what you're finding from looking at those policies at the university level on ChatGPT.
Yeah, I try to set up like a machine learning or model to predict like other universities, policy with their attitude towards ChatGPT used in university or institution. So,
all right, would love to hear more about that. Let's talk more about that at the end. I think that's a cool, kind of a meta example. It's like machine learning model about machine learning. That's kind of meta, right?
Yeah, try to set up, but I'm newer in machine learning. I got to learn more, so I'm coming here. So
yeah, cool. Thank you. Thanks for sharing that example. That's a great way. So a few more details on supervised machine learning. Requires coded data or data with a known outcome. That's a really important distinction. The basic process is you use use the coded or the outcome data, which you could call training data, to train an algorithm, which you could call a model, which you could call a predictive model, which you could call a machine learning model. Lots of synonyms here, and I want to not have those be barriers, but rather point out when words functionally mean the same thing or mean the exact same thing. So we could replace this with model or prediction model or machine learning model, and I think the meaning would be the same. We can use that algorithm to predict the codes or outcomes for new data. This is a really, really key point. Like if there's a key conceptual point in this whole 1 hour we're spending together, I think it's these 6 words here. To predict new data, data that's not used during the training. So if we used our model to predict data that was used to train the model, just on the face of it, that becomes sort of circular and seeming invalid. And I think in most cases it is. The model would probably have a pretty good sense of what the prediction should be because it was trained on it. And at an extreme, at a limit, the model can perfectly predict any outcome for data that was used to train it. So it's really important that we evaluate how good our model is using data not used during the training. And just to look ahead, I don't mean to foreshadow too much, but just to look ahead, The way we evaluate typically the goodness, the predictive utility of a machine learning model is give it new data, but don't show the model the outcome. Give the already trained model new data, don't show it the outcome. Use that model or algorithm to predict the outcome, and then just literally compare them. Here, oh, the model got it right. Here, the model got it wrong. Here, the model got it right. Here, the model got it right. And just sort of sum up over all of those predictions next to the known outcomes, how well the model did. And that can give you a sense for how well the model will do with any new data in the real world, so to speak, in other applications beyond those that have to do with the specific data you use to train the model. I want to pause there just because that's such a key point, even though we're just in the very beginning of the discussion. Okay, happy to talk. Well, we will talk more about that. One other important conceptual thing I just want to put out there is, importantly, a machine learning model can take the form of a classification model where you're predicting a dichotomous or a categorical outcome. In other words, dichotomous, yes, no, pass, fail, 1, 0, or categorical, A, B, C, D, E, A, B, C. Or a regression where you're predicting a number. This is a really common misconception that a machine learning model is only for classification. It's only for predicting whether someone passes or fails, or whether the next word in this paragraph is this particular word, or you can think of any number of examples. But importantly, it's just as valid in every possible sense to use a machine learning model to predict something like a score from 0 to 1,000, or percentage of final points earned, or any other continuous outcome. There's no profound principled difference between these two forms of a machine learning model. Algorithms include, I think it's really, this is one of my favorite things to emphasize in this module.
Joshua,
yeah,
Dr. Joshua, please, can you again elaborate a little more again on the classification and regression?
Yeah, sure. So our models of any kind can have different outcome variable types. So everybody's likely familiar with a linear regression where we're predicting a continuous outcome, or let's call it a dependent variable, or a logistic regression where we're predicting a dichotomous dependent variable, or a categorical variable, which is a little bit less common, but you could call that an outcome that you could model with a multinomial logistic regression. And so when people think machine learning, they think, oh, I'm predicting whether or not somebody will have this disease, or whether or not a student will pass this class, or whether or not I'll like this restaurant. And yes, those are all examples of supervised machine learning models, and we would call them classification models because we're predicting a dichotomous or a categorical outcome. But a machine learning model can also be used to predict a number. You're interested in the total number of points students will earn in a semester, or you're interested, in your case, Clement, Clement, in whether like a health score or something like that. You can use a machine learning model to predict a number. Literally, is this person's, I'm going to make this up. Sorry, Clement, I'm not a health researcher. We have this maybe aggregate health score that ranges from 0 to 1,000, where 1,000 indicates the best possible health and 0, very poor health. You could predict whether that number for a specific person is 912 or 850 or 500. That's an example of machine learning as well, even though the dependent variable is a number rather than a category, as in the case of what we'd call a classification model.
Okay. Thank you.
You're welcome. Thank you for asking that. So I think this is important too. One of my favorite things to emphasize is that a linear regression and a logistic regression are supervised machine learning models, or the algorithms for them. Many machine learning books start off with these models or even simpler models. And I've never seen a machine learning book that doesn't include them. So I think this is really important just to emphasize that the difference between the models we've used before and machine learning models is not so much about the algorithm, it's about what our goal is in using them and how we interpret them. And we'll get more into that later, but you can absolutely use a logistic regression for machine learning. I will stand by that claim, and I will point you to a lot of studies in education research and in other fields using logistic regressions to do it. And I think it's because there's a more profound difference, not not having to do with the specific type of the model. Other common algorithms include random forest, neural network, and other models used for even more complex things. How do you know which algorithm to choose? We will talk more about that in later learning labs. Okay, what kind of coded data? Just a few examples in ed research, assessment data, data from log files, open-ended written responses. I'll just point out, if any of you are interested in using text data, it's very common to use text data in supervised machine learning applications. And in fact, there is a great book, Supervised Machine Learning with Text Data in R, that's available freely on the web. If you're interested in that particular topic. I know many folks are, especially if you participated in the text mining learning labs. This might be a really nice bridge. Julia Silgi is the creator of the Tidy Text R package. And so this is a really nice bridge if you did some work with text over the summer. This book's great too. It goes into everything from very simple models to some very complex deep learning models, dense neural networks, convolutional neural networks, fancy schmancy stuff. Okay, so we have a discussion here. We've been discussing throughout, which has been great. This is where I think some of our best conversations came up in the summer. So I'm kind of debating in my mind whether we should invest the time in this now. Kind of leaning toward doing it. It's already 3:30 though. How about this? For the sake of time, I was going to do breakout rooms, but just for the sake of time, and it's 3:30. Everyone's probably a little tired. Could you maybe drop an example, if you don't mind, if you wish, of supervised machine learning in the context of ed research? We sort of did this earlier, but what's an example and why does it count as machine learning? So before, Megan, you provided an example. You asked what we thought. Alfredo agreed. Now it's your turn to defend your answer. So provide an example and then defend it. Say why it counts as, I'll even add a word here, supervised machine learning. Discuss why this counts as supervised machine learning. So if you can drop an example into the chat, that would be a nice way to engage with this idea. No wrong answers. In fact, wrong answers are celebrated, or what you think are wrong answers. So anything's good. Put it out there. Alfredo mentions early alerts because they predict if a student will succeed in the class based on early or midterm data. Alfredo, do you see these in your institution? Have you used these? I hear these are increasingly common in some universities, and that there's even some systems that have become.
I've seen them. I've seen them used in LMS integration of highlighting students that are at risk. And then I've seen it in publisher material where they highlight students as in terms of performance or how they're using the assignments provided to them in the LMS of the publisher. And then they start, hey, this might be a green risk, yellow risk, and red risk. And data starts coming in as soon as the third week, and they're already lighting them up.
Whew, there's like half of my brain, maybe some of you share this with me, that's like, oh, that's so cool. What a great example of like data science and machine learning. And then there's half of my brain that's like, oh my gosh, these systems are maybe so biased and like, I don't want to be classified this way. And how can these be misused? And they're like both occupying equal space in my brain.
The idea,
I think it's a great example.
The idea of how I used it, for instance, is to connect with those students that are being identified as high risk. Traditionally, the reason why they are high risk is not so much because they are not performing, it's rather they are not engaging. So if they're not entering the LMS, if they're not going through the whole assignment or, whatever engagement activity or whatever it is that I have done, it starts telling them, hey, these are the risks of a student in this, based on this performance.
Cool. I'm pretty comfortable with that as you described it. That seems like it keeps you as a human centered in the process, and you can have a discussion with students, try to engage them more. Cool, great. Clement mentions age of patients at diagnosis. Megan expanded on moats a little bit.
Sorry, I did not read the question well before I wrote that, so I was out of the context of education.
That's okay.
So, yes.
That's
My
okay.
next is predicting the time spent on assignment. So that's when I read the question, I refer to that.
Oh, there's educational research. I see. Okay, well, thanks
Yeah.
for adhering to the letter of the question there. No problem. Yeah, there's that P word predicting. Wei mentions ed researchers can use supervised machine learning to create automated assignment grading systems. That seems like a pretty ripe area for research and development over the next 5 or so years. Andy mentions predicting what students qualify for gifted programming. Yeah, cool example. Great. Any other examples are still welcome in the chat. Feel free to drop them in. No need. Thank you all for sharing, those of you who shared. Great. Some good examples that demonstrate getting a grasp on this focus of the supervised machine learning bucket. One thing, just because this is just a couple hours we have together here, I was looking ahead, there's that unsupervised bucket, and that's a methodology or a data analysis set of techniques for when we don't have an outcome or coded data. What do we do then? It's a technique to discover what those outcomes might be. So that's the focus of the fourth learning lab, just looking ahead. If you have a question where you might have data where you don't have an outcome yet, that might be a better bucket for you to spend some time in. Okay, I'm going to try to go quick through this just because the data is something you'll engage with over the next 4 machine learning labs if you wish. I mentioned this already. OULAD was created by some early learning analytics researchers. Many students pass the courses, but like any course or most courses, not all students do. We have data on students' initial characteristics and what they do in the course. So if you go to the OULAD website, by the way, for anyone teaching learning analytics or data science or machine learning, this is such a great data set because it's well documented, it's pretty interesting, it's from real students, it's freely available. You can download the whole data set here. It's pretty big. I think it's on the order of a gigabyte. And this is the schema, which for me, it took me like 2 hours of staring at this before it made any sense. But long story short, there's 7 files. These are the 7 files that you'll get when you download the data, and you'll get these as CSV files. And then these are the variables in each of those 7 files. And then these are descriptions of each of the variables. So it's enough to really go on for teaching. And importantly, a lot of people still publish off the OULAD data. So even though it's often used for teaching, you can use it just as an available data set for your own research if you wish. I'll stop there. It's joining the data together is kind of the one, not challenge, but just key step to make it work. Okay, so the kind of premise of this this learning lab, thanks, Hanwei. The kind of premise of this learning lab is that if we could develop a good prediction model, like Alfredo was mentioning, we could provide additional supports to students who need it, and maybe move the needle on some students succeeding who might not otherwise. So that's the connection to examples that you'll see in the learning analytics literature. For this first learning lab in the code along, if we do that, we'll focus on 3 files: student info, courses, and student registration. And just to get us focused on creating a machine learning model in this learning lab, there's a file in the GitHub repository titled this that just joins together these 3 files so that in this learning lab, we can work with a single CSV file. But just for transparency, if you're wondering, like, how do we get to this data? I don't see that in the Open University Learning Analytics data set. It's because this one file was used to join them. Pretty simple, just joining in R, but just want to mention that. Okay, one last thing I'll mention just is that we have this laser framework, which applies to many analyses: prepare for the analysis, prepare and wrangle the data, which might include data preparation. So this is more preparing for the project as a whole. Do some exploratory analysis, model the data, and then communicate what you found. There's a specific framework that is the focus of the first 3 learning labs, and this is consistent across all 3. And you can think of these as all being a part of this 4th step of modeling the data. Although they touch on other parts of the learning, the laser framework as well. So the first step is to split the data. That's so that we can see how good our model is later on. That's that step where we hold some of the I'll dive into that more in a bit, actually. It's better to get into later. But we take our data and we split it into what's called a training data set and a testing data set. Training data sets used to train the data model. Test data set is used to see how good the model is. Second step, we engineer features.
I'm sorry to interrupt, Josh. Is that akin to like an EFA and a CFA?
Good question. Can you say a little bit more? Are you thinking like if you use 2 different data sets for those 2 things?
Or when you're splitting your data set in an exploratory way, and then you're confirming it with the second set of the second half of your data.
If you used 2 different data sets, I would say it's very similar at a conceptual level.
Okay.
If you're using the same data set, I would say it's similar, but maybe I'm not sure. Yeah, I guess that would
or maybe it's more like with when you're doing reliability work and you're trying to split. I think I understand where you're going with it. I just was thinking of it conceptually as one is generating theory, the other's testing it, right? So
yeah, okay, good. I like the way you put it. Yeah, I'm on board with that.
okay.
I think there is a nice connection there. I'm trying to think through the specifics of whether it's like the same like statistically in terms of the underlying ideas, and I think I'm not sure, but I think
I didn't mean it statistically. I meant it more conceptually. Yeah.
Okay, that's okay.
Okay.
Yeah, sorry, all good. Yeah, I'm on the same page as you, Megan. I think that's a good connection to make. Same basic thinking. Second step, engineer features. So you can think of this as figuring out what your variables are. Sometimes your features are already engineered for you. Sometimes you need to create them. This can get really interesting and fun. So the example that we'll play with later on in a different learning lab is like if you have a timestamp, how do you add the timestamp to your model? There's a lot of options. You could add it as in a lot of different ways. Just to start you thinking, you could extract a variable, a feature from the timestamp that's for the day of the week. There could be differences in some outcome based on the day of the week of the timestamp, the hour of the day, even the minute within a specific hour, or the year. There's a lot of different features you could extract from a single variable. That's the underlying idea. This becomes even more important with more complex data like image data, where there's a lot of potential features you could add from an image beyond just the individual pixels for a particular individual values for the pixels in a grid that makes up the image that you're using as your data. Next, specify the model. So literally specify what the type of algorithm you're using, whether it's a linear regression or a random forest or a neural network. Then fit the model. Press a button, have your computer do a bunch of things to train the model or fit it. That's a synonym there. And then see how well the model, see how good the model is. See how good the model is. And I would say by accuracy, I don't mean just an accuracy statistic, but rather evaluate the predictive goodness would be a broader way of putting it. Okay. So in this learning lab, we're going to focus on a linear logistic regression to predict a yes or no outcome. This is to get us familiar with the process more, because the process in terms of those 5 steps and how we see how good our model is the same across the 3 learning labs for supervised machine learning and across different algorithms or types of models. It will be a bad model to start us off, but it will be a bad model that we can use to benchmark better models and to build better models kind of in after doing so. Okay, just one key point here is that we don't focus on inference or explanation. So if you're like me, you're coming to this thinking about effect sizes and p-values and standard errors and confidence intervals, and none of those apply. Instead, we use other metrics to evaluate what makes for a good model. And those have to do with metrics for the predictive goodness, how good of a prediction model our model is. So you can still, of course, use those measures of how good your model is for a logistic regression or a linear regression, but they don't have much utility when it comes to seeing how good of a prediction model our model is. They might be correlated with a good prediction model, but they're not direct measures of it. Okay, and then lots of big ideas, I know, and sorry for talking so much at this stage, but my AirPods out. Okay, a key concept is training and testing data, as was alluded to just a second ago. And so training data is data we use to fit a model, and then testing data is data we use to see how well our model did. So this is the key takeaway. By splitting our data into these two different sets, we can get a good sense of how good our model is at predicting data on new cases after training our model. And this can get into a lot of weeds here, and it relates to this idea in machine learning of how generalizable our model is. But in principle, if we have a data set that comes from the same population and it's a random sample, or to put it differently, if the data that we have in our test set is similar to other new data that we'll see in the world, and if both of those are similar but not the same as the training data that we used to fit our model, then how well our model does with that test data set that we split aside, back to Megan's point earlier about splitting our data into training and testing and trying to see, kind of confirm how good our model is. We can have a good sense of that how well our model does with that test data is how well the model will do with any new data that the model sees. There's a lot of limits to that and nuances to that. And in fact, this generalizability question is a big and active one in the machine learning field. Often in practice, in reality, machine learning models do worse when they're put into practice or used in the real world than we think, based on how well they do in the test data. But in principle, that's the whole point of using this test data, is to give us a sense of how well the model will do in the world. In other words, we can obtain an unbiased sense of how good of a prediction model our model is. Okay, we're next in the code along phase. And let me just take a quick informal poll in the chat. How many of you have R and can like open it up right now? I'm trying to get a sense of who wants to follow along, if all of you do or some of you. Cool. Oh, sorry. Mia, I see you talking, but I didn't hear you, which meant my audio was too low. Can you do you mind saying that again? Just sorry, someone mind talking. I want to make sure I have audio. I'm not hearing anyone. I'm not. Sorry. Thanks, Alfredo. Let me try.
Can you hear
I'm
us,
not.
Josh?
Sorry. Thanks, Alfredo. Let me try. No, I can't. There we go. Sorry about that. Thanks. Okie doke. So what I'm gonna do then is open up RStudio, and what we'll do is basically talk through and run this code in RStudio. That's the big picture plan. So we've got 5 steps corresponding to those 5 steps in the supervised machine learning framework, and we'll copy this code and run it. That's the goal here. Before we do that, can we take a quick maybe a 3-minute break? 3:55. I'm gonna grab some water, get RStudio open. We'll come back and run this, and then after that we can roll right into that open time where you all can share ideas for studies. We can talk through any specific questions you have about machine learning. Anyone who disagrees, please voice your disagreement. All right.
Fine with me.
All right. Thanks, Clement. Sounds good. Take a 3-minute break here. Uh-oh. Dog attack. You must sit. Anyone, anyone a dog owner? I'm a new dog owner. It's a lot of fun and a lot of work. All right. Hey everyone. Can you hear me still? All good? We'll get started in just a minute. Can you sit down, Goofy? She just had a surgery this last week. So she's been inside a lot, resting up. Over here. Oops, sorry. Alrighty. Hey everyone, welcome back. Thanks for the quick break. All right, so I am going to first clean up our studio a little bit. I get nervous when I see all these things open. So I'm going to restart R, and then I'm going to make a new file. Can you all see my screen here? Yeah, cool. All right, I'm going to do file, new file, R script. So file, new file, and then R script. Let me just look for the dog emoji to respond to Mia. All right, good. Okay, so you can follow along here. And the easiest way is just copy this code. And you can save it if you like. I don't like seeing that red color there. After years of using R, I don't like the look of an unsaved file. So I'm just going to save this here. LL1, 20, you can save it as whatever you want. Okay, and then the way I like to run code in an R script is to hold down Control and click Return. Control, Return, Control, Return. Oops, Sadie, come here, goofball. Sadie, come here. Just to run the code line by line that way. And then we're going to be using Star Wars data, which is built-in data. So it's kind of a fun data set for teaching, if anyone, if you're teaching a data science class or something in R. And it's got a lot of it's got several variables, about 87 different characters in Star Wars. So you probably have gotten this instilled into you by now that it's good to look at the data once you've loaded it, or in this case, just typed it since it's built in. Can you let me type? She's not letting me get to my button to get my pipe typed. I like to just view the data. So starting here, we got Luke Skywalker, 170. You can find out what the units are if you type question Star Wars, the name of the data set. We can sort the data too. We can see Jabba here is extremely massive. Rats Tyrell is very small. Anyway, that's our data set. We want to try, just for this code along, this is different obviously than the OULAD data, just to get familiar here with the process. Let's see if we can predict whether or not the species of one of these Star Wars characters is a human or not. And can we do it on the basis of other measured variables? So that's the question we'll be exploring. We have to do a little bit of data wrangling here, just to recode this species variable into a new variable called species human, where if species is equivalent to human, in other words, if the row has for this column human, then have this new variable be equal to human. And then otherwise, if that's not the case, have it be equal to not human. So when we then, oops, this should be species human. If we then count up the values in that variable, we should see that we have about roughly, very roughly, half human and non-human. Good enough for just getting familiar with the process. All right, anyone have challenges with this step here? This first couple of lines of code, or questions about it? All right, so far so good. So we can move on to the next step. Next, we'll split the data. This here controls, specifies what proportion of the cases go in the training data. So therefore, 20% of the data goes into the testing data set. You might be wondering, how do you determine what that value should be? There's no answer. I think one thing to think about is if you have a relatively small data set, this number could be larger so that you can use more data in your training data. Here you can see when we look at data train, that we only have 60 some cases in that data set. If this were like a half and half split, that would be an even smaller number. You can ignore that error, by the way. It's some weird glitch. Oops. Anyway, so that's why that's 80 in this case, but you'll see different rules of thumb for that. Okay, so this then just creates those two different data sets after we've basically added some metadata to the data to specify which are randomly sampled into training, which are randomly sampled into testing. Next, we'll do the most basic possible feature engineering. This is a really simple model just to get familiar with the process. Let's see if we can predict whether or not the Star Wars character is a human based on their height and mass. That's all that this line of code is doing here. And this is called a recipe. In more sophisticated and frankly, in real models, this will be a lot more complex. You can do things like standardize these variables, or you can dummy code them if they're categorical variables. There's a lot of different ways you can do the, no problem, Alfredo. Thanks for joining today. I'll share the recording. Yeah, I'll be sure to share that. So this is just very simplified just for this example today. Next, we'll specify the model and workflow. So here we're saying we have a logistic regression. We will use the GLM package, which is built into R, or GLM functions, I think. This almost seems unnecessary since we've already specified logistic regression, but some models you can use in regression or classification mode, back to our earlier conversation. So here we'll just say, to be explicit, we're specifying a classification model. And then this step you can think of as just telling R how to put everything together. So take your model. Hey, Sadie, come here, goofball. Sadie, come. Can we sit, please? Sorry. Thank you for understanding. Take our model and recipe, put them together, and we're ready to fit the model, which is what we do in this fourth step. So this is actually mechanically fitting the model. This is if you're doing using a neural network or something, this is what can take a while. None of these other steps should take very long in most cases. This can take as many as, minutes up to hours in most cases that you would be using R to fit a machine learning model on your computer for. And then this last step is a little bit weird, and it might seem a little unnecessary given that we've just fit a single model to a single training data set. This becomes more useful when we are doing something we'll talk about later called cross-validation, where we fit actually many models as a way to get more from our training data. So we'll talk more about that later. For now, just kind of consider it to be a required step. And then in the very last step, this is that fifth step where we see how well our model did. We see how well our model did. Sorry, one more thing to add here. What this is doing is using our trained model to make predictions using the test data. So you can think of this as a step that involves both the training data and the testing data, both of our splits of our data. And then here we'll see how well our model did in terms of here just accuracy of our predictions for whether or not the data that happened to be in data train, the 43 cases, I think, were a human or not. So anyone care to venture a guess for this? This is simply accuracy, just like you might be familiar with from like qualitative coding and comparing like two coders. What does this mean about how accurate our model is?
Like, you're talking about the accuracy binary that you've highlighted up there.
Yeah, sorry. Yep, this number right here.
Like weakly associated. Like weakly.
Yeah, I was pretty disappointed. In fact, I think because the data set's so small, you might see a very different number on your computer, just due to random sampling variation. Can anyone share in chat what number you got if you ran all of these steps?
Oh, I got tied up on mine.
No problem. Just as your others are sharing, this means that 36.7% of the time the model predicted whether or not the Star Wars character was a human accurately. Very bad. Like that's a almost in no cases would that be good enough to trust. Less than half of the time. In fact, the model would probably do better if it just predicted all of the time that the species was a human. So
question, did it use all of the inputs and all of the columns?
Good question, Megan. Because of what we said here,
Oh, there.
Only 2 of the inputs, just height and mass. It did not use skin color, hair color, eye color, birth year, sex, gender, homeworld, what films they were in, vehicles. So we could build a much better model by doing what you just implied we could do, add more variables. And or features that we extract from those variables. And then B, specify a more sophisticated model than a logistic regression. But I mean, big picture, we're talking about a 87 row data set. So there's only so much we can do in terms of the sophistication of the model.
Sure.
But yeah, that's exactly the way you should be thinking about like, how can I make this model better? That's so brilliant insight into what we can do next.
A side note, I use stars. I do a undergrad class for classroom assessment, and I make a fake data set with Star Wars characters.
Oh, do you really?
Yeah, and I assign them all like Kylo Ren gets oppositional defiant disorder. Like,
oh, cool.
And then so anyway, this is kind of fun to see this set.
I don't know Star Wars well enough to know why that character would have oppositional defiant disorder, but it seems like a fun.
Oh well, he's the angry trope against his dad, and so
got it.
So it's just a way for these undergrads to they import the fake data set on assessments they design, and they try to like predict pre-post growth on this hypothetical class that they've got.
That sounds fun.
Yeah, it's fun.
Joshua, I have a question.
Yeah, sure.
Yes, my question is, okay, let's say I'm trying to make a prediction model. For instance, like age, patient age at diagnosis. So can I use the same code and just change, some of the parameter to match the patient and get the same thing, similar prediction?
Yeah, in principle, I mean, change the name of the data, do any steps here that you need to do to recode variables, Clement, and then specify the variables you want to use, back to Megan's point, as predictors. Here we're just using 2 of them. There's more you can add. You might want to recode them in some way or dummy code them, process them. But yeah, in principle, absolutely. You could just reuse this with your data.
Oh, okay. Thank you. Wonderful.
Yeah, you're welcome. Yeah, I mean, and one cool thing, just to wrap up here, is that these steps are common to all supervised machine learning applications, including whether you're using supervised machine learning with text or neural network with image data. It's the same basic process. That's kind of the cool thing about this tidy models approach, is that we can reuse these same core pieces. So that's it. That's machine learning. We're making a prediction. Anyone get a better prediction than 36%? I remember in the summer, someone just due to random chance, sometimes these were as high as like 80, 90%. The model did really badly for me.
Yeah, I run that as well. Mine is, let me see. I think.
There you go. I got 63%.
Yeah, mine is 0.58%.
0. Okay. 58, yeah.
and the second one is 22 or 0.
22. Oh, that's horrendous.
Yeah, zero. My here is 0.22, and the first one is 0.59.
Oh, I see. That one's okay. Yeah, this is a different metric. 0.5. Okay, so that's about what.
I mean, like, does it, I would imagine it makes a difference in the way you're splitting it too.
Yeah, it should. I think absolutely. Just it's such a small
Okay.
and yeah, I mean there it's a little higher, Megan. Maybe there's more training data. The model's picking up on more of the relations between height and weight. Yeah,
This summer we put what planet in and it changed it completely because that was a better predictor of if they were human or not.
Sense.
interesting. Yeah.
It was
Okay,
like
I'm not a Star Wars
Homeland
person.
here, I
Yeah,
guess.
which are some of these like very obviously human planets?
Gosh. My teenage son would be disappointed in my failure to answer that.
We could do counting up the cross tabulation. Thanks, Andy. I'll share the recording later. Thanks for joining. What was it? Human species? What was it again?
Species underscores human. Yeah, you got it right.
How did that not work? Oh, Star Wars Recoded. It doesn't matter. But yeah, that's funny. Yeah. Yeah, we could probably build a really good model. Maybe too good.
There's your frequency distribution. Okay.
Tatooine is a human place, it seems. Anyway, okay, so back to it. So just to segue out of this, one thing that often people wonder about machine learning is how large your sample needs to be. I would say bigger than this, but not as big as you might think. One thing I like to push back on is people thinking that for machine learning you need thousands or tens of thousands or even more rows of data. In principle, it's very similar to the inferential statistics issue of how large your sample needs to be able to make an inference. So do you need a sample of 30 cases? Yeah, maybe for some very simple questions that might be enough. How about 20 cases? I don't know. In some cases that could be enough. How about 10? Yeah, that's probably too few in most cases. How about 100? Yeah, that's good for some questions. There's no one right answer is the point. And it's similar for supervised machine learning. There's not any kind of cutoff. More is often better, just like for our inferential statistics use cases. But if someone says like, oh, you need 400 or more cases for supervised machine learning, you could push back on them and ask them on what principle basis that's the case. I think often these are rules of thumb that have some utility, but there's not any deep reason why our sample needs to be a certain size. Often we'll have better accuracy with a larger sample of data, and often we can have a better sense of how well the model will perform in the real world with a larger sample. But these things aren't fixed. But this is probably too small, so there's a limit to that. This is seeming too small, especially with us having such incredibly high sampling variability. Okay, so just a quick reflection as well, you know what, let's roll into the Q&A. I'll just kind of mention here that this is a common question, is like, why can we not just evaluate how good our model is with the training data? We sort of foreshadowed earlier why that might not be good, and you can imagine a model that's so complex that the model basically is trained to look for a specific series of values for an individual observation and to predict a certain outcome based on it. So at the limit, you could just train a perfect model that does really terribly in the real world because it might not have ever seen in its training data like the data it will see. So this relates to this bias variance trade-off that we'll talk about later too. But this is why it's important, or the answers to this question are why it's important to split our data into testing and training sets. There's a really nice reading, some of you might have read already, on an early paper distinguishing inferential modeling from predictive modeling. And there's a walkthrough in this book, chapter 14, on machine learning, although it doesn't use the tidy models code that we used here. It used an older R package called Caret, C-A-R-E-T. Case study walks through these 5 steps. A key is available. There's some troubleshooting steps. It's a nice way to elaborate on these steps. And one thing I just really want to emphasize, Clement, to you and others, is that, yeah, these are the core steps involved in machine learning. The next 2 learning labs add detail and nuance. There's tons to learn for me and for you. But in principle, this is it. There's not really any big difference. There's some, again, nuance and detail and that kind of thing, but not anything principally different.
I've been reflecting on, and you can probably name this problem, which is it seems like the training models are only as good as the coding that was initially there.
Yeah.
And so is there something I can read up on about this phenomenon of, like, in the case of the divergent thinking tasks, maybe we only had moderately strong interclass coefficients for graders. So, is this something I can read about?
I think you're onto something, Megan, in that this is an important and common challenge. And so I think in this paper here, I think they get into like our inter-rater human to human agreement was like 0.8, and that's therefore good enough to train a model with that. But as you're suggesting, that means there's still error, in other words, bias, in those codes, and you're then feeding that into the model. What does that mean? Yeah, it's a really big question. I don't have one answer. I think this paper might be a starting point, but I think there's a lot of depth there, and I think probably a lot of different ways to think about it, but not one right answer for like, this is, you must have a, agreement of 0.85 or point whatever.
It's usually some rules of thumb, right?
Yes. Yes. Yes.
Cool. I'll pull this. This is exactly what I was looking for.
Great. Yeah. I think of this as a great example of a common machine learning application in science ed research, my field. It's not necessarily a great model, but I think it's a great example. And I think it's like the kind of best case scenario, which is still often back to like the very beginning of this, like often not that great. Like these models, even with the best possible, these are leaders in the field, training an army of undergrads and grad students to qualitatively code these with the highest possible inter-rater agreement. And the models are still kind of okay in a lot of cases. So this is hard, like all things that are complex, or most things that are complex. There's also a nice paper, Megan, just real quick, on bias in machine learning that's sort of related to your point, but a little different.
Yeah. Yeah, this is great.
I'm trying to think, where is it? It's a nice paper in science education. Where is it? Tina's been publishing a lot. There it is. Can AI be racist? Yeah.
Oh, cool.
I think the answer is a definitive yes. They can be.
Of course.
There's that paper there.
Oh, that's fascinating.
Yeah, great questions. Thanks. So yeah, that's it for the presentation. Like to wrap up, like to summarize, supervised machine learning is about making predictions. There's some cool, hey, stop eating that. There's some cool innovations that machine learning methodologists have developed so that we can train a prediction model and see how good it does in a valid way. And that's basically what these steps are: splitting the data, evaluating accuracy. So that's the first thing. Hey, Sadie, come here. Sorry, I'm gonna pause myself for a second.
No, get it. I've got dogs too. Let's see. The trade-off for being in such beautiful weather.
It looks totally sunny and wonderful where he is.
Well, I am definitely in this very hot southern Florida, and I'm pining for colors and crispiness and wearing jeans and sweaters.
I'll be jealous of your Florida weather come like January, Megan, so it'll come around.
Yeah. Well, hurricanes aside, it has its good months.
Yeah. So happy to wrap up, happy to answer questions.
So I want to ask a personal question about a project I have. But if
great.
people have general questions, they can go first.
Well, I'll let you go. I'm working on an ASIL proposal. So, and I think a bunch of you all will be at AECT. Have fun.
Good luck on the proposal, Megan. Thanks for joining today.
Thank you.
Sorry. Before the kiddos get home. Sorry, one second.
You're good.
I love my neighborhood. Also I always get kiddos
All right.
next door.
Thank you so much. I really appreciate the presentation. Thank you so much.
Yeah, you're welcome, Clement. Feel free to reach out as you work to adapt that code for your own
Uh,
model.
All right. Thank you. Good night.
Yeah, you're welcome. Hey, Mia, you said you had a question about your about a study. I'd love to hear about it.
Yeah, so we have a survey that we developed to measures a teacher's sense of agency for science instruction. And I'm trying to figure out so we ran a confirmatory factor analysis, and I've been messing around with structural equation modeling, but what we're trying to figure out, there's 6 constructs that identify like their level of agency. I don't know if you can call the level, but that identify agency. And then there's 4 like identified actions or expressions of agency. And so, like, for example, do they teach with a justice orientation? And so we'd like to be able to use this survey to predict that like action of agency, right? And so I don't know if this is something that would be appropriate, to use what we're learning here with you as a predictive model for those actions, or if I should just stick with the other stats.
Yeah, cool. So do you have data that you have coded for those different levels of agency and those actions?
Yes, so 1,600 people
Wow.
filled out the survey, so we ended up with a lot of data. So I'm trying to figure out how to, yeah, I mean, so I was gonna play around and put it into what we did today and just see like what happens, but I don't know. I just, from your opinion, like is using machine learning to make our predictive model, like is that appropriate, or am I just doing it just to do it and I should use something else?
Yeah, good question. So great question. Thanks for bringing this example. It's a really good one. Do you have aspirations of using that prediction model in the future for other respondents of the survey?
Yes, that's the intent. So that if we, so like if a teacher, took or we had a group of teachers or whatever who took the survey, then I don't know if we've been calling it a score, but I don't know if it is a score. But their like score on this survey is that like so if they, I guess what we're wanting to see if we can figure out is if they score a certain number on the survey, is that predictive of them actually applying these expressions of agency in their classroom?
Okay, and do you have data? I think I know the answer to one of these is yes, but I'll just ask it anyway. Do you have data on both what you can collect from the survey, and then B, what they actually do in the classroom? You have data on both of those things?
We do. So we have 4 different, like, are they like renegotiating their identity? Are they, like pushing back against, in their space to bring in science education, those kinds of, so we have four expressions.
Yeah.
But they were all self-report. So we didn't do observations or anything like that, but we have, so it was all contained in the one survey, but we have like, it's 2 parts. So there's 6 constructs identifying agency, and then 4 pieces identifying their expressions of agency.
Okay, got it. Thanks. Now I see all those pieces tied together. Cool.
Yeah.
So So in the future, you could ask people about their sorry, what was the first thing again? Not expressions of agency, but rather their
they're like, I totally lost the word. Like their perceptions, that's not the
Yeah.
right word, but they're, like their um oh my gosh, I can't think of the word, but it's like perceptions. We'll go with perceptions for now.
Okay, well that's fine for the purpose of methodologically sorting it out. Okay, so
Right.
so their perceptions would you in the future, like let's say a hypothetical use case a year from now, would you not also ask them about their actions, the way that second bucket of things you measured, the things they report doing in their classroom at the same time?
Mhm. Yeah, we could. Like that's so it's all right now, it's all in one survey, right?
Yeah.
But we were talking about like could we, if we knew what their sense of agency was, would that predict them actually, applying things in their science classroom?
Yeah.
And I don't know that anybody even cares. Like I was just trying to like figure out what I'm doing and how it fits with machine learning.
Yeah,
But
yeah. No, it's good. It's good. I think um I no, it's a great example. I think it almost would be a good example to work up into like future materials just because it gets at the heart of why we might use machine learning or why we might not use it.
okay.
My first thought just from talking through this is that if you had a measure getting at something you suggested a second ago, if you had a measure of some kind of classroom like implementation, like those expressions of agency,
Mm-hmm.
and let's say those were really costly to measure, like it was hard to get into classes, it took a lot of time, that kind of thing. And in
Okay.
the future you wouldn't be able to do that, then I'm wondering like if you could train a model based on that data so that in the future you just need those survey responses, the first bucket of things, the perceptions of agency, and you
Mm-hmm.
could then make a prediction about what they would actually do, and that could be interesting and useful for different reasons. But if they're both from the same survey, it sounds at the margin in terms of the benefit of this approach and the cost of using it. It seems more like something like SEM or some kind of regression model where you're interested in the predictive utility, but you could also get at that through estimating a coefficient that relates those perceptions to those actions. And you could
Okay.
report what those are and sort of see what those are for each sample. Because I think if you use that model as a prediction model with new data in the future, it wouldn't tell you much different than what you could get from just asking them, hey, what do you do in the classroom? And if it made predictions, you could maybe compare those predictions to what they say, but it's unless you it's not adding up in my mind how that would give you much more than what you would get from a
Right.
nice like regression model like that.
Okay, no, that totally makes sense of talking it through with you. Yeah. So I'm like in the middle of the SEM stuff right now, trying to work through that. So okay, so that makes sense. So we'll just keep doing that. But all right, I might play around with this though, just as a practice then.
I mean,
with
it'd be interesting to see like how just as practice or maybe see if there's something there that you could expand with, maybe if I could say maybe different data in the future, maybe something on implementation. So then it's like you're in that scale up bucket. It's like, oh, we spent all this time to develop this prediction model. Now we can use it just using survey data and we can predict what teachers will do in their classroom. That's where you seem to get more juice from the squeeze there.
Yeah, okay.
It's a great example. It kind of gets at the heart of some of the tensions that I've been thinking through and we've been working on in the lab.
All right. Well, very cool. Thank you so much for the information and
Yeah,
for running these sessions. I know you guys give up a lot of time to do all this.
no,
So.
thanks for the appreciation. Yeah, please follow up with the results of that study. I'd be happy to hear what you find if you don't mind emailing me at some point, or if you have any questions,
Yeah.
happy to talk to them.
For sure. All right.
Cool. All right. Thanks, Mia.
Thanks. Take care.